Hello, and welcome to Velorin Sleepy Space Mysteries, a quiet place where the universe slows down just enough for us to drift through its oldest secrets together. Before we begin tonight's journey, I'd love to know something simple. Where in the world are you listening from tonight? And what time is it where you are? Some of you may be under midnight skies, others resting in the soft glow of early morning. Yet wherever you are, we're all sharing the same vast universe above us. And if you enjoy these peaceful journeys through space, consider subscribing to the channel, leaving a gentle like, and ringing the little bell so you won't miss future cosmic explorations. It helps more curious dreamers find their way here. Now, take a slow breath, let your shoulders relax, and allow your mind to drift outward into the deep cosmos. Not long ago on this channel, we explored the mysterious story of the first stars that ever ignited in the universe. Those ancient lights changed everything. But tonight we go even further back, to the quiet moment before galaxies existed at all. Because galaxies, those enormous swirling cities of stars, had to begin somewhere. And their story begins in a universe that looked nothing like the one we see today. About 13.8 billion years ago, the cosmos was astonishingly small, dense, and unimaginably hot. This was the moment we now call the Big Bang. Despite the dramatic name, it wasn't really an explosion in space. Instead, it was the expansion of space itself, stretching outward in every direction. At first, the universe was filled with a chaotic sea of particles. Quarks, electrons, and photons danced through a blazing cosmic fog. But as the universe expanded, it cooled. Slowly, patiently, matter began to organize itself. Hydrogen formed, then helium, simple atoms that would one day become the building blocks of stars, planets, and eventually us. About 380,000 years later, something extraordinary happened. Light, which had been trapped inside the dense early universe, was finally able to travel freely. This ancient light still fills the cosmos today as the cosmic microwave background, a faint afterglow of the universe's birth. And yet, despite this glow, the universe remained dark. No stars, no galaxies, just an immense ocean of gas stretching across space. This era would become known as the Cosmic Dark Ages. But hidden inside that quiet darkness were tiny imperfections, barely noticeable ripples in the distribution of matter. Small differences, almost nothing at all. Yet these faint irregularities would eventually grow into the greatest structures in existence. Clusters of galaxies, superclusters, and the spiraling stellar cities that fill the night sky. So the question that quietly guides our journey tonight is this: how did the first galaxies ever come to be born in the cosmos? To answer that, we must travel into the long silent era when the universe was still gathering itself together, preparing for the first sparks of starlight. But before we continue drifting through the deep past of the cosmos, take a moment to subscribe if you enjoy these calm space mysteries, and let me know in the comments where you're listening from tonight, your little corner of Earth, connected to this vast universe. Now, let's continue our journey. For a very long time after the universe cooled enough for atoms to form, the cosmos remained strangely quiet. The great expansion that began at the Big Bang continued steadily, stretching space wider and wider, but light itself had largely disappeared from the stage. There were still photons traveling through space, remnants of the early universe, but there were no stars yet to illuminate the darkness. If you could somehow drift through this ancient era, you would find yourself floating in an immense, cold ocean of hydrogen and helium gas. There would be no glowing galaxies in the distance, no constellations, no shimmering rivers of starlight, just darkness, patience, and time. This period is what astronomers call the cosmic dark ages, though the name sounds far more dramatic than the reality. There were no castles, no dragons, no ancient battles unfolding across space. Instead, there was simply a universe waiting. Neutral hydrogen gas filled nearly every corner of existence like a thin, invisible fog. Gravity, the quiet sculptor of the cosmos, had already begun its work. It was pulling matter together, slowly amplifying those tiny ripples we mentioned earlier, the faint irregularities in the density of the early universe. These fluctuations were unimaginably small at first. In some places, matter was only slightly denser than the surrounding regions, perhaps by just a tiny fraction of a percent. Yet gravity does not require large differences to begin its patient work. Wherever matter gathered even slightly, gravity pulled more of it inward. Over millions of years, those regions grew heavier, drawing in surrounding gas like dew forming on an invisible web. Something else was helping guide this process as well, something we cannot see directly but whose presence is written everywhere in the structure of the cosmos. This mysterious ingredient is known as dark matter. Unlike ordinary matter, dark matter does not emit or absorb light. It remains completely invisible to telescopes. Yet its gravitational influence is enormous. In fact, there appears to be far more dark matter in the universe than ordinary matter. Long before the first stars formed, dark matter had already begun arranging itself into a vast three-dimensional framework known as the cosmic web. Imagine a gigantic spider web stretching across billions of light years. Along the thin filaments of this web, matter slowly accumulated. At the intersections of these filaments, gravity became especially strong, gathering gas into growing knots and clumps. These dense regions would eventually become the birthplaces of galaxies, but for now they were simply dark clouds drifting through a silent universe. Inside these clouds, the temperature was cold by cosmic standards, and the gas moved slowly. Hydrogen atoms collided gently, drifting past one another like particles in a calm mist. But gravity was steadily compressing the gas. As more material fell inward, the pressure at the center of these clouds gradually increased. Over millions of years, the gas became denser and hotter. The universe, without any hurry at all, was preparing the conditions necessary for something extraordinary. Creating a star requires a delicate balance of forces. Gravity must compress gas strongly enough that temperatures rise to millions of degrees. Only at such extreme conditions can hydrogen nuclei begin to fuse together, releasing enormous energy. That energy becomes starlight. But in the early universe, there were no heavy elements like carbon, oxygen, or iron to help gas clouds cool efficiently. Everything consisted almost entirely of hydrogen and helium. This meant that early clouds had to grow extremely massive before they could collapse enough to ignite. Slowly, patiently, gravity continued its quiet work. One cloud here, another there, each one drifting deeper into collapse. Tens of millions of years passed, then hundreds of millions, and somewhere within one of those dense knots of matter, the temperature finally climbed high enough. Hydrogen nuclei began to collide with such intensity that they fused together, forming helium and releasing tremendous energy in the process. In that moment, the darkness of the universe was pierced for the first time since its earliest beginnings. A star had been born, but this was no ordinary star like the sun we know today. These first stars belonged to a class astronomers call Population 3 stars. They were giants, far more massive than most modern stars, sometimes hundreds of times the mass of our sun. Because they contained only the simplest elements, they burned incredibly hot and lived astonishingly short lives. Their brilliant light poured into the surrounding darkness like the first lanterns in a vast cosmic wilderness. For the first time in hundreds of millions of years, the universe was no longer completely dark. Yet this was only the beginning. One star became a cluster, clusters began forming small stellar communities, and slowly the first faint outlines of something larger began to appear. The earliest ancestors of galaxies were beginning to take shape within the ancient cosmos. The birth of that first star did more than simply add a point of light to the darkness. It marked the beginning of a transformation that would slowly reshape the entire universe. For hundreds of millions of years, the cosmos had existed in quiet shadow, filled with neutral hydrogen gas that absorbed and scattered energetic light. But now, inside the brilliant furnace of a newborn star, something powerful had begun. Nuclear fusion was turning hydrogen into helium, releasing immense radiation that streamed outward in all directions. Around the star, the surrounding hydrogen fog began to change. The energetic ultraviolet light stripped electrons from the hydrogen atoms, turning neutral gas into ionized plasma. This process, known as reionization, slowly cleared the ancient fog that had filled the universe since the cosmic dark ages began. At first, the change was small. One star illuminated only a tiny bubble around itself, like a lantern glowing inside a vast night forest. But stars rarely form alone. Within the dense gas clouds that had collapsed under gravity, many massive stars began to ignite almost at the same time. Their combined light expanded these glowing bubbles farther and farther into the surrounding darkness. As more stars formed across the cosmos, these bubbles grew and eventually began to overlap, gradually transforming the universe from opaque darkness into a transparent sea where light could travel freely again. Yet these first stars were very different from the stars we see today. Because they formed from nearly pure hydrogen and helium, they lacked the heavier elements that modern stars contain. This difference had profound consequences for how they lived and died. Without heavier elements to regulate their internal processes, the earliest stars burned their fuel with incredible intensity. Many of them were enormous, perhaps 100 or even several hundred times the mass of the sun. Such massive stars produce staggering amounts of light and heat, but they also consume their fuel extremely quickly. Some may have lived only a few million years, a brief flicker on the cosmic timescale. When these giants reached the end of their short lives, they did not fade quietly. Instead, many exploded in powerful supernovae, blasting newly created elements out into space. Inside their cores, nuclear reactions had forged heavier atoms such as carbon, oxygen, silicon, and iron. When the star exploded, these elements were scattered across surrounding gas clouds, enriching the cosmic environment for the next generation of stars. This moment was one of the most important turning points in the history of the universe. Before the first stars died, the cosmos contained almost nothing but hydrogen and helium. Afterward, it began to fill with the raw ingredients needed to build planets, complex chemistry, and eventually life itself. Every atom of carbon in your body, every atom of oxygen you breathe, was once created in the heart of a star that lived and died long before our solar system existed. The universe was slowly becoming more complex. But these first stellar explosions did something else as well. Their powerful shock waves compressed nearby gas clouds, triggering new waves of star formation. Regions that had once been quiet began to sparkle with clusters of newly ignited stars. These clusters, bound together by gravity, became the earliest stellar communities in the cosmos. They were not yet the grand spiral galaxies we recognize today. Instead, they were smaller, irregular groupings of stars and gas, sometimes called proto-galaxies. Imagine small islands of light scattered across an immense dark ocean. Each island contained thousands or perhaps millions of stars, gravitationally bound together and slowly growing as they attracted more gas from their surroundings. Over time, these small stellar systems continued to evolve. Some merged with neighboring clusters, combining their stars and gas into larger structures. Others drifted along the invisible filaments of the cosmic web, guided by the gravitational pull of dark matter. The cosmic web itself played a crucial role in shaping the earliest galaxies. Those vast filaments of dark matter formed the scaffolding upon which ordinary matter collected. Gas flowed along these gravitational highways, feeding the growing proto-galaxies located at the intersections of the web. In these dense hubs, star formation accelerated. More gas meant more collapsing clouds, more stars igniting, and more supernovae enriching the environment with heavier elements. Slowly, through countless mergers and bursts of star formation, the first recognizable galaxies began to emerge. Yet the universe was still a chaotic place. Young galaxies were often irregular and turbulent, their shapes distorted by constant interactions with neighboring systems. Gas clouds collided, stars were flung into new orbits, and gravitational tides stretched galaxies into strange and beautiful forms. But beneath all this apparent disorder, a deeper pattern was beginning to appear. Gravity was quietly organizing the cosmos into structures of increasing size and complexity. What had once been tiny fluctuations in the early universe were now growing into vast cosmic systems. And the small islands of stars scattered across space were slowly transforming into something much larger. The first true galaxies were beginning to take shape within the ancient cosmos. As more of these early stellar communities appeared across the young universe, something remarkable began to happen. The scattered islands of stars did not remain isolated forever. Gravity, which had already gathered the first clouds of gas, continued its quiet work on a much larger scale. Every cluster of stars exerted a gravitational pull on its surroundings, drawing in additional gas, dark matter, and sometimes even neighboring clusters. Over millions of years, these interactions slowly transformed the small proto-galaxies into larger and more complex systems. It was not a neat or orderly process. The early cosmos was more like a construction site than a finished city. Gas clouds drifted along the filaments of the cosmic web, colliding and merging with growing stellar groups. Sometimes two proto-galaxies would approach one another, their gravitational fields tugging and stretching each other's shapes long before they actually merged. Streams of stars could be pulled away like glowing ribbons, tracing graceful arcs through space. When the two systems finally combined, their stars mixed together, their gas clouds collided, and new bursts of star formation ignited. In this way, galaxies did not simply appear fully formed. They grew piece by piece, gathering material through a long history of mergers and accumulation. The cosmic web continued to guide this process. Along its vast filaments, matter flowed slowly but steadily toward the densest intersections. These intersections became the busiest neighborhoods of the early universe, places where gas was plentiful and gravitational forces were strongest. Proto-galaxies located in these regions grew rapidly, feeding on streams of gas that poured in along the dark matter filaments. Fresh material meant more collapsing clouds, and more collapsing clouds meant more stars lighting up the growing structures. Yet even as these systems expanded, their shapes remained irregular. The graceful spirals and smooth elliptical forms familiar to modern astronomy had not yet emerged. Young galaxies looked chaotic, like glowing clumps of stars tangled within clouds of gas and dust. Their internal motions were turbulent, their structures unstable. Stars formed rapidly in some regions while other areas remained dark and quiet. Astronomers studying the earliest galaxies today often describe them as clumpy, a word that captures both their youth and their unfinished nature. But within this turbulence, patterns slowly began to develop. As gas settled into rotating disks around the densest regions of dark matter halos, angular momentum started shaping the overall structure. Rotation helped flatten some galaxies into thin disks, while others remained more spherical depending on their history of collisions. The delicate balance between gravity pulling inward and rotational motion spreading material outward would eventually determine whether a galaxy developed spiral arms or settled into a rounder form. Another quiet transformation was taking place as well. With each generation of stars that lived and died, the chemical composition of the universe was gradually changing. The first stars had formed from almost pure hydrogen and helium, but their explosive deaths scattered heavier elements into surrounding space. New gas clouds incorporated these elements, allowing them to cool more efficiently and collapse more easily. This meant that later generations of stars could form in greater numbers and with more diverse properties. The universe was slowly becoming chemically richer, layering complexity upon complexity. As this process continued, Some proto-galaxies became large enough to host hundreds of millions or even billions of stars. Their gravitational pull grew stronger, allowing them to retain more gas and sustain long periods of star formation. These expanding stellar cities were the earliest recognizable galaxies, though they still looked quite different from the elegant spirals seen in nearby space today. In many cases, their shapes were distorted by frequent encounters with neighboring systems. The early universe was crowded, and galaxies often lived close enough to influence each other's evolution. But this crowded environment also accelerated their growth. When galaxies merged, their combined gravity pulled in additional gas from surrounding space, fueling even more star formation. Each merger reshaped the galaxy's structure, mixing old stars with new ones and redistributing gas throughout the system. Over time, repeated mergers could transform a chaotic protogalaxy into a more stable and massive structure. Gradually, the universe was filling with these growing systems of stars. What had once been a dark sea of gas was becoming a network of luminous islands, each one containing countless suns. And although the earliest galaxies were still rough and unrefined, they represented a crucial step in the cosmic story. The universe had moved beyond its silent beginning. Light was spreading, structures were forming, and the first great stellar cities were beginning to claim their places within the vast architecture of the cosmos. As these early galaxies continued growing within the cosmic web, their environments became increasingly dynamic. Streams of gas flowed steadily along the dark matter filaments, feeding the young galaxies like invisible rivers delivering fuel to distant cities. Wherever this gas accumulated, gravity would begin compressing it once again, creating new stellar nurseries inside the galaxies themselves. Giant clouds of hydrogen and helium drifted through these growing systems, gradually collapsing under their own weight. Within the densest regions, new stars ignited in clusters, lighting the surrounding gas with brilliant radiation. Some of these stellar nurseries produced hundreds or even thousands of stars at once, forming dazzling groups that would remain gravitationally bound for billions of years. These clusters became some of the oldest surviving structures in many galaxies, silent witnesses to the earliest chapters of cosmic history. But the same forces that created stars could also reshape entire galaxies. As galaxies drifted along the filaments of the cosmic web, they frequently encountered one another. These encounters rarely involved direct collisions between individual stars, because stars are separated by enormous distances. Instead, the galaxies interacted through gravity. When two galaxies passed close to each other, their gravitational fields tugged at the distribution of stars and gas inside each system. Long streams of stars could be stretched outward into space, forming delicate arcs that trailed behind the galaxies like glowing threads. Gas clouds inside the galaxies were even more strongly affected. When these clouds collided or compressed during gravitational encounters, they triggered intense bursts of star formation known as starbursts. During such periods, a galaxy might form new stars dozens or even hundreds of times faster than usual, briefly illuminating itself with the brilliant glow of thousands of young suns. These interactions played a crucial role in shaping the appearance of galaxies. Some systems experienced relatively calm histories, accumulating gas gradually and forming stars in a steady rhythm. Others endured repeated mergers with neighboring galaxies, each encounter stirring their contents and redistributing their stars into new orbits. The balance between these two paths began determining the broad categories of galaxies that would eventually populate the universe. In galaxies where gas settled into rotating disks without too many disruptive collisions, a remarkable structure began to emerge. As the galaxy rotated, waves of density moved through the disk, compressing gas in certain regions and triggering new star formation along curved paths. Over time, these patterns developed into the graceful spiral arms we recognize in many galaxies today. Stars continuously moved through these spiral patterns, entering regions of dense gas where new stars were born and then drifting outward again as they orbited the galactic center. Other galaxies followed a very different evolutionary path. When two large galaxies merged, the orderly rotation of their disks could be disrupted completely. The gravitational chaos scattered stars into many different directions, leaving them orbiting in random paths rather than along a flat rotating plane. The gas inside these galaxies was often used up rapidly during starburst events or expelled by powerful stellar winds and supernova explosions. Without large amounts of gas remaining to form new stars, these systems gradually settled into smoother, rounder shapes known as elliptical galaxies. Their stars aged quietly over billions of years, glowing with a softer reddish light as they slowly exhausted their nuclear fuel. Meanwhile, some galaxies remained irregular, their structures shaped by ongoing interactions or by the turbulent environments in which they formed. These irregular galaxies often contained large reservoirs of gas and continued forming stars vigorously. Their shapes could appear distorted or asymmetrical, reflecting the complex gravitational influences surrounding them. Although they might look chaotic compared with elegant spiral galaxies, irregular galaxies were important laboratories for understanding how stars continued forming in environments rich with gas. By this stage in cosmic history, the universe had changed dramatically from its quiet beginnings. Instead of a dark ocean of gas, space had become populated with countless galaxies, each one containing vast numbers of stars. These galaxies were not isolated islands, however. They gathered together into groups and clusters, drawn by gravity into larger communities that spanned millions of light years. Within these clusters, galaxies orbited one another, occasionally merging and reshaping their structures once again. Yet beneath all of this visible activity lay a deeper, invisible architecture. The dark matter halos surrounding galaxies continued to dominate their gravitational behavior, binding their stars together and guiding their motions through space. Without these halos, the stars within galaxies would move too quickly and drift away. Instead, the dark matter provided the hidden mass necessary to hold each galaxy together, ensuring that these vast stellar systems could survive for billions of years. And so the first galaxies, once just faint clusters of stars emerging from darkness, had grown into enduring structures within the cosmos. Their formation marked one of the most profound transitions in the history of the universe. The cosmic dark ages had ended. Light now filled the expanding universe, carried by billions of stars gathered into galaxies that continued evolving colliding, and growing. But even as these early galaxies matured, their story was far from finished. The forces that created them were still at work, quietly shaping their futures and guiding them toward even greater structures within the cosmic web. By now, the universe had changed in ways that would have been impossible to imagine during the long silence of the cosmic dark ages. What was once an endless, dim fog of hydrogen had transformed into a landscape filled with glowing structures. Galaxies were appearing across the expanding cosmos, scattered along the filaments of the cosmic web like lanterns hung along invisible threads. Yet these early galaxies were still young, still evolving, and still far from the graceful forms we recognize today. Inside them, star formation continued shaping their futures. Massive clouds of gas drifted through galactic disks and halos, collapsing again and again under the persistent pull of gravity. Every time a cloud collapsed, new stars were born. Some were small and stable, destined to shine for billions of years. Others were massive and brilliant, burning intensely before ending their lives in spectacular supernova explosions. Each generation of stars enriched the surrounding gas with heavier elements, allowing future stars to form more efficiently. The universe was slowly becoming chemically complex, layering new ingredients into the cosmic mixture. This ongoing cycle of birth and death created a kind of cosmic recycling system. Stars formed from gas, lived their luminous lives, and eventually returned much of their material to space through stellar winds or explosive deaths. That recycled gas then cooled, condensed, and formed new stars once again. Over time, galaxies became rich environments filled with many generations of stars, each generation slightly different from the last. Some galaxies formed stars rapidly, glowing with the blue light of young stellar populations. Others gradually slowed their star formation as their gas supplies diminished, leaving behind older stars that glowed softly with warmer hues. But the evolution of galaxies was never shaped by star formation alone. The environment surrounding each galaxy also played a crucial role. Many galaxies lived close to others, orbiting within groups and clusters where gravitational interactions were common. When galaxies passed near one another, their gravitational fields could distort their shapes, pulling long streams of stars outward or funneling gas toward their centers. In some cases, these encounters triggered new waves of star formation, while in others they slowly stripped gas away, leaving galaxies quieter and more mature. Meanwhile, at the very centers of many growing galaxies, another powerful influence had begun to emerge. Deep within their cores, enormous black holes were forming and growing alongside the galaxies themselves. These supermassive black holes, containing millions or even billions of times the mass of the Sun, remained invisible directly, but their effects were profound. As gas spiraled toward these black holes, it heated to extraordinary temperatures, releasing tremendous energy. This energy could push gas outward, slowing or even stopping star formation in parts of the galaxy. In this way, the growth of black holes and the evolution of galaxies became closely linked, each influencing the other over vast stretches of cosmic time. Beyond the galaxies themselves, the larger structure of the universe continued developing. Galaxies gathered into clusters, and clusters gathered into even larger structures called superclusters. These immense assemblies of galaxies stretched across tens or hundreds of millions of light years. Between them lay enormous voids where very few galaxies formed at all. The universe had developed a kind of grand architecture, a pattern of filaments, nodes, and empty spaces shaped by the subtle but relentless pull of gravity acting over billions of years. And through all of this, the expansion of the universe continued. Space itself kept stretching outward, carrying galaxies farther apart over time. Some galaxies remained bound together by gravity, forming stable groups that would orbit each other for billions of years. Others slowly drifted away from one another, their light taking longer and longer to cross the widening distances between them. Looking back across this vast history, it is remarkable to remember how small the beginnings truly were. The seeds of galaxies were nothing more than tiny ripples in the density of the early universe. Almost imperceptible differences spread across the young cosmos. Yet those tiny variations, amplified by gravity and guided by dark matter, eventually grew into the enormous galaxies we see today. Each galaxy became a vast system of stars, gas, dust, dark matter, and sometimes powerful black holes, all bound together by gravity and evolving over billions of years. So the first galaxies were not created in a single dramatic moment. They emerged slowly, patiently, through countless generations of stars, mergers, and cosmic flows of gas. The quiet ripples of the early universe had grown into luminous cities of stars scattered across space. And as the universe continued expanding and evolving, these galaxies would keep changing, merging, and shaping the cosmic landscape for billions of years to come. The long darkness of the early cosmos had finally given way to light, structure, and motion. The age of galaxies had begun, and the universe was no longer a silent expanse of gas, but a living network of stellar worlds, each one carrying forward the story that had started with the first faint sparks of starlight. By the time the first galaxies had emerged from the quiet darkness of the early universe, the cosmos had begun to resemble something far more complex than the simple sea of hydrogen that once filled it. Yet, even these first galaxies were only the earliest drafts of much grander structures still to come. They were small compared with many modern galaxies, and their shapes were often chaotic, constantly reshaped by the gravitational environment surrounding them. The universe at this stage was still crowded and energetic. Galaxies were forming rapidly, and they were rarely left alone for long. One of the most important forces shaping their evolution was the simple fact that galaxies move. Every galaxy drifts through space, guided by the gravitational landscape of the cosmic web. Some travel slowly along the filaments of dark matter, while others orbit within dense groups of neighboring galaxies. Over time, these motions bring galaxies close enough to influence one another. Sometimes the encounter is gentle, a slow gravitational tug that distorts their shapes slightly before they drift apart again. Other times the encounter leads to something much more dramatic, a merger. When two galaxies approach each other, their gravitational fields begin interacting long before their stars ever mix together. Each galaxy pulls on the other, stretching its shape and redistributing its gas and stars. Long tidal streams of stars can be pulled outward, forming luminous arcs that trail behind the galaxies like glowing ribbons in space. Inside the galaxies themselves, enormous clouds of gas may collide and compress. This compression often triggers bursts of new star formation, lighting up regions of the galaxy with brilliant clusters of young stars. Eventually, the two galaxies may spiral inward toward one another, slowly merging into a single larger system. This process can take hundreds of millions of years, unfolding so gradually that no single moment marks the exact instant when one galaxy becomes another. Instead, their stars mix together over time, settling into new orbits as gravity reshapes the combined structure. In the early universe, these mergers were especially common. Because galaxies were smaller and more numerous, the distances between them were often relatively short compared with the vast scales we see today. This meant that galaxies frequently collided and merged, gradually building larger and more massive systems. Many of the galaxies we observe in the present-day universe grew through this process, assembling their stars from the remains of many smaller ancestors. During these mergers, the delicate rotational patterns that might have existed in the original galaxies were often disrupted. Stars that once orbited in orderly disks could be thrown into random trajectories, creating more spherical distributions of stars. Over time, repeated mergers could transform a once chaotic cluster of stars into a smoother, rounder galaxy known as an elliptical galaxy. These systems contain vast numbers of stars but often have very little gas remaining to form new ones. In other cases, galaxies avoided major collisions for long enough that their gas was able to settle into rotating disks. Within these disks, the rotation of the galaxy played a crucial role in shaping its structure. As gas and stars orbited the galactic center, waves of density moved through the disk, compressing gas in certain regions. These compressed regions became fertile ground for star formation, lighting up curved bands of young stars that traced elegant spiral patterns. These spiral galaxies became some of the most beautiful structures in the universe. Their bright arms wrapped around glowing central cores, creating shapes that resemble vast cosmic pinwheels turning slowly through space. Our own galaxy, the Milky Way, would eventually become one of these spiral systems, though its formation would take billions of years and involve many mergers with smaller galaxies along the way. Yet, even as spiral galaxies formed, the universe continued evolving on larger scales. Galaxies rarely existed in isolation. Most were part of small groups, gravitational families of galaxies orbiting one another through space. Some groups contained only a few members, while others formed massive clusters containing hundreds or even thousands of galaxies bound together by gravity. Within these clusters, galaxies could interact repeatedly over cosmic time. Some would merge into larger galaxies. Others would lose gas through repeated gravitational encounters, gradually becoming quieter systems with little star formation remaining. The environment of a galaxy often determined how it would evolve, shaping its structure and the kinds of stars it would contain. Despite all this complexity, the fundamental processes that began during the cosmic dark ages were still guiding the story. Gravity continued pulling matter together. gas continued forming stars. Dark matter continued providing the invisible framework holding galaxies together. What began as tiny ripples in the early universe had grown into enormous stellar cities, each containing billions of stars. And yet the story of galaxies was still far from finished. The universe would continue reshaping them through collisions, growth, and slow cosmic change for billions of years to come. As galaxies continued growing through mergers and steady streams of incoming gas, their internal structures began slowly stabilizing. The early chaos of constant collisions gradually gave way, in some regions of the universe, to more organized motion. Stars that had once been flung through space in unpredictable paths began settling into gravitational patterns that would persist for billions of years. Inside many galaxies, rotation became one of the most important organizing forces. When large amounts of gas fell toward the center of a galaxy, conservation of motion caused that gas to spin faster as it contracted inward. Over time, this rotation flattened the gas into wide disks that surrounded the galactic core like enormous spinning plates. Within these disks, star formation continued shaping the galaxy's appearance. Vast clouds of gas orbited the galactic center while slowly cooling and collapsing into new stars. These clouds did not collapse uniformly. Instead, they were influenced by subtle waves of density moving through the rotating disk. As these waves passed through the gas, they compressed it slightly, encouraging the formation of new stars along specific curved paths. Over millions of years, those curved regions filled with young, bright stars, creating the glowing spiral arms that would eventually define spiral galaxies. These arms were not rigid structures made of the same stars forever. Instead, they behaved more like patterns in a flowing river, where stars drifted through the arms as they orbited the galaxy. Young stars formed inside the spiral arms often shone with brilliant blue light, illuminating the surrounding gas clouds and dust lanes. Their intense radiation carved glowing cavities in the gas, while stellar winds pushed material outward into space. Eventually, many of these massive stars ended their lives as supernovae, scattering heavy elements into the galactic environment once again. In this way, spiral galaxies became vibrant regions of ongoing star birth, constantly renewing themselves with fresh generations of stars. But not every galaxy enjoyed such a steady and peaceful evolution. Many galaxies lived in crowded cosmic neighborhoods where interactions were unavoidable. Inside large galaxy clusters, gravitational forces from neighboring galaxies could disrupt delicate rotating disks. Repeated encounters might strip gas from galaxies as they passed near one another, leaving them with little material to form new stars. Over time, these galaxies gradually faded into systems dominated by older stars. When two galaxies of similar size merged, the result could be especially dramatic. Their rotating disks might be completely disrupted as their stars were thrown into new orbits. The combined system often lost its flattened structure and instead settled into a more rounded shape where stars orbited in many different directions. This process frequently produced elliptical galaxies, vast stellar systems containing hundreds of billions of stars but very little gas left to form new ones. These galaxies became quieter places over time, glowing mostly with the warm light of aging stars. Even within these quieter galaxies, however, the memory of their violent past remained hidden in the motions of their stars. Astronomers studying elliptical galaxies today often find subtle traces of ancient mergers, streams of stars that once belonged to smaller galaxies long ago absorbed. These faint stellar rivers drift through the larger galaxy like ghostly reminders of its earlier history. Meanwhile, spiral galaxies that avoided major disruptions continued developing their elegant structures. Over billions of years, their spiral arms became more defined, shaped by the balance between gravity pulling inward and rotational motion spreading stars outward. Many spiral galaxies also developed central bulges, dense concentrations of older stars surrounding their cores. At the very center of these bulges, supermassive black holes often grew quietly, their immense gravity influencing the motion of nearby stars. Gas flowing toward these central regions sometimes triggered intense bursts of star formation near the galactic core. In other cases, material falling toward the central black hole heated up dramatically, releasing enormous energy that could push gas away from the center. This process helped regulate how quickly new stars could form in different regions of the galaxy. While individual galaxies were evolving internally, the larger cosmic landscape was becoming increasingly structured. Galaxies gathered into clusters containing hundreds or thousands of members bound together by gravity. These clusters were among the largest gravitationally bound structures in the universe. Inside them, galaxies orbited through vast halos of dark matter and extremely hot gas that filled the space between galaxies. Beyond clusters lay even greater structures known as superclusters, immense regions of the universe where many clusters and groups of galaxies were linked together along the filaments of the cosmic web. When astronomers map the distribution of galaxies across enormous distances, they see a pattern resembling foam or a giant three-dimensional web, with galaxies tracing the bright strands while vast empty voids stretch between them. This grand cosmic architecture had begun with the faintest ripples in the early universe. Now those ripples had grown into a universe filled with structure on every scale, from individual stars to galaxies, from clusters to superclusters. And through all of it, galaxies continued drifting, merging, and evolving as gravity quietly guided their long journeys through the expanding cosmos. As the universe continued aging through billions of years, galaxies were no longer just isolated experiments of gravity and gas. They had become stable cosmic ecosystems, each with its own history written in stars. Yet even while many galaxies matured, the universe itself remained restless. Motion never truly stopped. Galaxies drifted through space like slow-moving ships on a vast cosmic ocean, guided by the invisible currents of gravity and dark matter. Sometimes those paths carried galaxies close enough that their stories would intertwine. When two galaxies passed near each other, the encounter rarely resembled a sudden crash. Instead, it unfolded as an elegant gravitational dance lasting hundreds of millions of years. As the galaxies approached, their mutual gravity began pulling on the distribution of stars within each system. Spiral arms could stretch outward like soft ribbons, while streams of stars were gently drawn away from their original homes. Astronomers call these structures tidal tails, and they can extend hundreds of thousands of light-years into space. Inside the galaxies, gas clouds experienced a different fate. While stars rarely collided with one another due to the enormous distances separating them, clouds of gas were much larger and more easily compressed. When galaxies interacted, these gas clouds often crashed together and slowed dramatically. The sudden compression triggered enormous waves of star formation. Entire regions of the galaxy could light up with brilliant clusters of young stars forming at extraordinary rates. Astronomers call these events starbursts, and during such periods a galaxy may produce stars dozens or even hundreds of times faster than usual. These starburst episodes could reshape the galaxy's appearance in dramatic ways. Bright young stars illuminated the surrounding gas with intense ultraviolet radiation, carving glowing nebulae across the galactic disk. Massive stars formed during these bursts lived short lives, exploding as supernovae and scattering heavy elements throughout the galaxy. The environment became chemically richer and more complex, preparing the galaxy for future generations of star formation. But galaxy interactions did more than trigger new stars. They also changed the overall structure of the galaxies themselves. As gravitational forces stirred their stars into new orbits, the delicate patterns of spiral arms could become distorted or even destroyed entirely. When two large spiral galaxies merged, the resulting system often lost its orderly rotating disk. Instead, the stars settled into random orbits around a shared center, creating the smooth, rounded shapes characteristic of elliptical galaxies. These elliptical galaxies became some of the largest stellar systems in the universe. Many contain trillions of stars, far more than typical spiral galaxies. Yet despite their immense size, they often appear calmer and more stable than their spiral counterparts. Most of their gas had already been used up or expelled during earlier bursts of star formation. Without fresh gas to collapse into new stars, elliptical galaxies slowly aged, glowing softly with the reddish light of older stellar populations. Meanwhile, other galaxies continued evolving along quieter paths. Spiral galaxies that avoided major collisions could maintain their rotating disks for billions of years. Within these disks, spiral arms persisted as long-lived patterns guiding star formation. Gas clouds entered these arms, collapsed into new stars, and eventually drifted away as they orbited the galactic center. The galaxy became a kind of self-sustaining engine, steadily producing new stars while recycling the remnants of older ones. Over time, spiral galaxies also developed complex internal structures. Many formed thick central bulges filled with older stars. Surrounding these bulges were extended disks containing younger stellar populations and glowing nebulae where stars continued to form. Beyond the visible disk stretched vast halos of older stars and dark matter, invisible to the eye but crucial for maintaining the galaxy's gravitational stability. Our own galaxy, the Milky Way, would eventually grow into such a spiral system. Its formation involved countless mergers with smaller galaxies early in its history. Some of those ancient companions were completely absorbed, their stars scattered into the Milky Way's halo. Others survived as small satellite galaxies that still orbit our galaxy today. Even now, the Milky Way continues slowly consuming smaller galaxies, incorporating their stars into its growing structure. This process of galactic growth through mergers and gradual accumulation is sometimes called hierarchical formation. In simple terms, it means that large galaxies are built from the remnants of many smaller ones. Just as cities grow by absorbing surrounding towns and villages, galaxies expand by pulling smaller systems into their gravitational embrace. When astronomers observe distant galaxies whose light has traveled billions of years to reach us, they often see this process still unfolding. Some galaxies appear stretched and distorted by recent interactions. Others display brilliant starburst regions where new stars are forming rapidly. These observations allow scientists to look back in time and witness the stages through which galaxies evolved. From the earliest proto-galaxies to the enormous stellar systems we see today, the rise of galaxies has been a story shaped by gravity, motion, and time. And while many galaxies now appear calm and stable, their histories remain written in the motions of their stars and the faint streams of light left behind by ancient mergers long ago. As galaxies matured across the universe, their appearances slowly began to reveal the long stories of their past. Every spiral arm, every glowing halo of stars, every distorted shape carried evidence of the forces that had shaped them. To the casual observer, galaxies might appear serene in photographs, floating quietly through space like delicate works of art. But beneath that calm appearance lies a history filled with motion, interaction, and constant change. Galaxies are not static structures. They are dynamic systems, evolving slowly but continuously across billions of years. One of the most powerful influences on a galaxy's evolution is its environment. A galaxy drifting alone in a relatively quiet region of space can maintain its structure for extremely long periods. Gas continues to flow gently through its disk, forming new stars in a slow and steady rhythm. Spiral arms remain well-defined, illuminated by bright clusters of young stars and glowing nebulae. In these calmer regions of the cosmos, galaxies have the opportunity to develop elegant structures that remain stable for billions of years. But not all galaxies enjoy such peaceful surroundings. Many reside in crowded galaxy clusters where the gravitational pull of neighboring systems is impossible to ignore. Inside these clusters, hundreds or even thousands of galaxies orbit a shared center of gravity. Their motions through space create an environment filled with constant gravitational influences. Galaxies passing near one another can distort each other's shapes, pull gas away from their disks, or trigger bursts of star formation as their gas clouds collide. In some cases, galaxies moving through dense clusters experience a phenomenon known as stripping. As a galaxy travels through the hot gas filling the cluster, pressure from this gas can slowly remove the galaxy's own gas reservoir. Over time, the galaxy loses the raw material needed to form new stars. What remains is a quieter system composed mostly of older stars, glowing with a softer reddish light. Astronomers often refer to these galaxies as red and quiet, because their periods of active star formation have largely come to an end. Even in these quieter galaxies, however, the influence of gravity continues shaping their internal structures. Stars orbit through the galaxy in complex paths, guided by the combined gravitational pull of visible matter and the massive halo of dark matter surrounding the system. Although dark matter remains invisible to telescopes, its presence is essential. Without the gravitational support of dark matter halos, galaxies would not be able to hold themselves together. Their stars would move too quickly and gradually drift away into intergalactic space. The central regions of galaxies also play an important role in their evolution. Deep within many galaxies lies a supermassive black hole, an object containing millions or even billions of times the mass of the Sun compressed into an incredibly small region. These black holes formed early in the history of galaxies and grew alongside them over billions of years. Although they occupy only a tiny portion of the galaxy's volume, their influence can extend far beyond their immediate surroundings. When gas falls toward a supermassive black hole, it forms a rapidly spinning disk that becomes extremely hot and luminous. This process can release enormous amounts of energy, sometimes producing powerful jets of energetic particles that shoot out from the galaxy's center at nearly the speed of light. These jets can travel thousands of light years into space, pushing gas away from the central regions of the galaxy and affecting how stars form in the surrounding environment. This interaction between galaxies and their central black holes is one of the most fascinating areas of modern astronomy. Observations suggest that the growth of a galaxy and the growth of its central black hole are closely connected. As the black hole feeds on incoming gas, it releases energy that can regulate the rate at which new stars form within the galaxy. In a sense, the black hole acts as a kind of cosmic thermostat, helping determine how active the galaxy remains over time. Beyond individual galaxies and clusters, the largest structures in the universe continued taking shape along the filaments of the cosmic web. Galaxy clusters themselves gathered into even larger structures called superclusters, enormous regions containing tens of thousands of galaxies bound together by gravity. Between these vast structures lay immense voids where very few galaxies existed at all. These empty regions stretched across tens of millions of light years, creating a cosmic landscape of bright filaments and dark expanses. When astronomers map the positions of galaxies across the observable universe, they see a remarkable pattern. Galaxies trace out a giant network of interconnected filaments, resembling foam or a three-dimensional web stretching across space. This cosmic web represents the large-scale architecture of the universe, shaped by the same gravitational processes that first amplified tiny density fluctuations shortly after the Big Bang. From the first faint clusters of stars to the enormous superclusters spanning hundreds of millions of light years, the rise of galaxies transformed the universe into a richly structured cosmos. Yet even with all this complexity, the forces guiding the story remained the same quiet actors that had been present from the beginning. Gravity pulling matter together, dark matter providing the invisible scaffolding, and time allowing the universe to slowly build its grand design. By the time the universe had reached several billion years of age, galaxies had become the dominant structures shaping the visible cosmos. What had begun as small clusters of stars forming inside dark matter halos had grown into enormous systems containing hundreds of billions of stars. Yet their evolution had not been simple or uniform. Every galaxy carried a unique history written in the motions of its stars, the distribution of its gas, and the faint traces of past interactions that astronomers continue to study today. One of the most fascinating things about galaxies is how their histories remain preserved long after the events themselves have passed. Even when a galaxy appears calm and stable, careful observation can reveal subtle evidence of ancient mergers. Long streams of stars sometimes stretch across the outer halos of galaxies, remnants of smaller galaxies that were pulled apart and absorbed billions of years ago. These stellar streams drift quietly through space, slowly dispersing but never entirely disappearing. They act like fossil records of cosmic history, allowing astronomers to reconstruct the events that helped build the galaxy we see today. Our own galaxy provides a remarkable example of this process. The Milky Way did not form all at once from a single cloud of gas. Instead, it assembled gradually through the merging of many smaller galaxies early in its history. Some of those ancient companions were completely absorbed, their stars now orbiting in the Milky Way's halo. Others survived as dwarf satellite galaxies that still circle our galaxy today. Even now, the Milky Way continues to interact with these companions, slowly pulling them apart through gravitational tides. One of the most striking examples is the Sagittarius dwarf galaxy. This small galaxy has been orbiting the Milky Way for billions of years, but with each pass it loses more of its stars to the gravitational pull of our much larger galaxy. Those stripped stars now form enormous looping streams that wrap around the Milky Way like faint ribbons. Over time, the remaining core of the Sagittarius dwarf galaxy will eventually dissolve completely, its stars becoming permanent members of the Milky Way. This process of galactic growth through mergers has shaped many of the large galaxies we observe today. In fact, some of the most massive galaxies in the universe are thought to have formed through repeated mergers over billions of years. Each merger adds more stars, more gas, and more dark matter to the growing system. At the same time, these events often reshape the galaxy's structure, turning spiral systems into elliptical ones or triggering bursts of star formation that briefly transform the galaxy's appearance. But even as galaxies merge and grow, the universe itself continues expanding. This expansion gradually increases the distances between galaxies that are not gravitationally bound to each other. Over extremely long periods of time, galaxies belonging to different groups and clusters drift farther apart as space itself stretches between them. In the distant future, galaxies outside our local gravitational neighborhood may eventually disappear from view entirely as their light becomes too stretched by cosmic expansion to reach us. For now, however, galaxies remain connected through the vast network of the cosmic web. Groups of galaxies gather into clusters, and clusters gather into superclusters, forming some of the largest structures in the universe. Within these environments, galaxies continue interacting, sometimes merging and sometimes simply passing near one another, subtly influencing each other's evolution. Throughout all of this activity, the underlying forces guiding the rise of galaxies remain the same ones that began shaping the cosmos shortly after the Big Bang. Gravity continues drawing matter together. Dark matter continues providing the invisible framework holding galaxies and clusters in place. And within galaxies themselves, the cycle of star formation continues, slowly transforming gas into stars, stars into heavier elements, and those elements into the raw material for future generations of stars and planets. The rise of galaxies represents one of the most remarkable chapters in the story of the universe. From the faint ripples in the density of the early cosmos to the immense stellar systems filling space today, galaxies are the result of billions of years of cosmic evolution. They are the cities of the universe, vast communities of stars where gravity, gas, and time work together to shape the cosmos. And yet their story does not end here. Even now, galaxies continue moving, merging, and evolving. New stars are still forming in countless stellar nurseries across the universe. Black holes at the centers of galaxies continue growing and influencing their surroundings. The cosmic web continues guiding the slow drift of galaxies across unimaginable distances. The universe is still building its grand structures. And to understand what truly holds these enormous systems together, we must now look beyond the visible stars themselves, toward the hidden forces that have quietly shaped galaxies since the very beginning. By the time galaxies had fully emerged across the universe, the night of the early cosmos had transformed into something rich with structure and motion. Billions of galaxies drifted through space, each containing vast populations of stars, clouds of gas, swirling dust, and mysterious forces shaping their evolution. From a distance they appeared calm, almost serene, glowing softly against the dark background of space. But behind that quiet beauty lay powerful forces working continuously to hold everything together. If we look closely at galaxies, a strange puzzle appears almost immediately. The stars within a galaxy are constantly moving, orbiting the galactic center at incredible speeds. In our own Milky Way, for example, the Sun travels around the center of the galaxy at roughly 200 kilometers per second. That is fast enough to circle the Earth several times in just a single minute. Yet despite these enormous speeds, the stars remain gravitationally bound within the galaxy rather than flying off into empty space. At first glance, this seems perfectly reasonable. Gravity from the galaxy's mass should keep the stars in orbit, just as the Sun's gravity keeps the planets of our solar system in place. But when astronomers began carefully measuring the motions of stars in distant galaxies, they discovered something unexpected. The outer stars of galaxies were moving far faster than the visible mass of the galaxy could account for. According to the laws of gravity, those stars should not be able to remain in orbit. They should gradually escape into intergalactic space. Yet they do not. This mystery led scientists to a remarkable conclusion. Galaxies must contain far more mass than we can see. Surrounding every galaxy is an enormous halo of invisible matter, extending far beyond the visible stars and gas. This mysterious substance does not emit light, does not absorb light, and does not interact with electromagnetic radiation in any direct way. Because of this, astronomers call it dark matter. Dark matter forms the hidden skeleton of the universe. Long before the first stars ignited, dark matter had already begun gathering into massive halos throughout space. Ordinary matter, the atoms that form stars and planets, fell into these halos under the influence of gravity. In this way, dark matter provided the gravitational wells that allowed galaxies to form in the first place. Without it, the small density fluctuations in the early universe might never have grown large enough to create galaxies at all. Even today, dark matter continues shaping the structure of galaxies. The stars we see shining in a spiral galaxy represent only a small fraction of its total mass. Most of the galaxy's gravitational strength comes from its surrounding halo of dark matter. This halo acts like a vast, invisible container, holding the galaxy together and preventing its stars from drifting away. Yet dark matter is only one of the unseen architects guiding the evolution of galaxies. Another powerful influence lies hidden in the centers of many galaxies themselves. Deep within their cores reside enormous black holes, objects so dense that their gravity prevents even light from escaping once it passes too close. These supermassive black holes can contain millions or even billions of times the mass of our Sun, all compressed into a region smaller than our solar system. For many years, astronomers believed these black holes were simply passive occupants of galactic centers, perhaps formed long after the galaxy itself had already developed. But modern observations have revealed something far more intriguing. The growth of galaxies and the growth of their central black holes appear to be closely connected. As gas flows toward the center of a galaxy, some of it feeds the black hole. When this happens, enormous amounts of energy can be released, heating surrounding gas and sometimes driving powerful outflows that push material back into interstellar space. These outflows can influence how quickly new stars form within the galaxy. If too much gas accumulates in the center, the black hole's energy may push some of it away, slowing star formation. In this way, the black hole helps regulate the growth of the galaxy itself, acting almost like a cosmic feedback system that keeps the galaxy from growing too quickly. So within every galaxy, a delicate balance unfolds. Dark matter holds the galaxy together. Gravity gathers gas into new stars. Supernova explosions recycle stellar material into the interstellar medium. And at the center, a supermassive black hole quietly influences the surrounding environment. Together, these forces shape the life of a galaxy across billions of years. The visible stars may capture our attention when we look up at the night sky, but they are only part of the story. Beneath the glowing beauty of galaxies lies an invisible framework of gravity and dark matter, guided by the quiet power of black holes. These unseen architects have been shaping the cosmos since the earliest moments after the Big Bang, and their influence continues even now, guiding the future of galaxies as they drift, collide, and evolve across the vast expanse of the universe. If we could somehow step far outside a galaxy and observe it from a truly distant vantage point, the first thing we might notice would be how fragile it seems. A spiral galaxy, for instance, stretches across hundreds of thousands of light-years, yet the stars inside it are separated by enormous distances. The space between them is vast and mostly empty. From this perspective, it might seem almost miraculous that galaxies manage to hold themselves together for billions of years. and yet they do, quietly maintaining their structure across cosmic time. The reason lies in the immense gravitational web created by dark matter halos. While the glowing stars form the visible face of a galaxy, the dark matter halo surrounding it is vastly larger and more massive. Imagine a luminous jellyfish drifting inside an enormous invisible bubble. The glowing tendrils of the jellyfish represent the stars and gas, while the invisible bubble surrounding it represents the dark matter halo. Without that halo, the stars inside the galaxy would not remain bound together. Their rapid orbital motions would gradually scatter them outward until the galaxy dissolved into a loose cloud of drifting stars. Astronomers cannot see dark matter directly, but its presence becomes unmistakable when they study the motions of stars. By measuring how quickly stars orbit the centers of galaxies, scientists can calculate how much gravitational pull must exist to keep those stars in place. Again and again, the results reveal the same surprising truth. The visible matter in galaxies is not nearly enough to explain the observed motions. Only by including large amounts of unseen mass do the calculations make sense. This hidden mass extends far beyond the bright edges of galaxies. The dark matter halo surrounding a galaxy can stretch several times farther than the visible disk of stars. Within this halo, smaller clumps of dark matter often exist as well. These smaller clumps can host dwarf galaxies, tiny companions that orbit the larger system like satellites. Many of the faint galaxies that circle the Milky Way today are thought to reside within such substructures of dark matter. Dark matter also shapes the large-scale architecture of the universe itself. Long before galaxies formed, dark matter had already begun gathering into filaments and dense nodes. Ordinary matter followed these invisible gravitational pathways, eventually forming galaxies at the intersections of the cosmic web. In this sense, dark matter acted like the scaffolding of a building long before the visible walls were constructed. Yet gravity and dark matter alone do not tell the whole story of how galaxies evolve. Another powerful influence lies hidden within the energetic hearts of many galaxies. At the center of these systems reside supermassive black holes whose gravitational pull can shape the behavior of surrounding matter on enormous scales. When gas drifts toward a galaxy's center, it does not fall directly into the black hole. Instead, it spirals inward, forming a rapidly rotating disk of extremely hot material known as an accretion disk. As this gas spirals closer and closer to the black hole, friction and compression heat it to extraordinary temperatures. The result is one of the brightest phenomena in the universe. Some of these central regions shine so intensely that they outshine the entire galaxy surrounding them. These luminous centers are known as active galactic nuclei. In extreme cases, they can power quasars, objects so bright they can be seen across billions of light-years of space. The energy released by matter falling toward the black hole can launch powerful jets of charged particles outward at nearly the speed of light. These jets extend far beyond the galaxy itself, sometimes stretching tens of thousands of light-years into intergalactic space. The energy carried by these jets and outflows can profoundly affect the galaxy that hosts the black hole. Gas that might otherwise collapse to form new stars can be heated or blown outward, temporarily halting star formation in certain regions. In other cases, The turbulence created by these outflows may compress gas clouds elsewhere in the galaxy, triggering new bursts of star formation. The relationship between black holes and galaxies is therefore deeply interconnected, each influencing the other over cosmic time. While these processes may sound violent, they unfold slowly on astronomical timescales. The growth of a black hole, the flow of gas through a galaxy, and the formation of new stars often take millions or billions of years to complete. From our human perspective, galaxies appear almost frozen in time, but in reality they are constantly evolving, guided by the invisible forces that have shaped the cosmos since its earliest moments. So when we look up at the night sky and see the faint glow of the Milky Way stretching across the darkness, we are witnessing only the visible surface of a much deeper structure. Beneath the shining stars lies an enormous halo of dark matter. At the center lurks a supermassive black hole quietly influencing the surrounding galaxy. And throughout the system, gravity continues its patient work, guiding stars through their orbits and shaping the galaxy's future. The universe may appear peaceful from afar, but behind its beauty lies an intricate balance of forces that have been sculpting galaxies since the beginning of time. Even with dark matter holding galaxies together and supermassive black holes shaping their central regions, the story of galaxies is still not entirely complete. The universe itself continues to evolve on scales far larger than any individual galaxy. In fact, galaxies are constantly moving through space, pulled along invisible gravitational currents created by the combined mass of surrounding structures. Although this motion unfolds slowly across millions of years, it means that galaxies are always approaching, drifting past, or sometimes colliding with one another. From a human perspective, the word collision might suggest something violent and catastrophic, but when galaxies meet, the event is surprisingly graceful. Because stars are separated by such enormous distances, the chance of two stars directly striking one another during a galactic encounter is incredibly small. Instead, what truly interacts are the gravitational fields of the galaxies themselves. As two galaxies approach, their gravity begins stretching and distorting each system long before their stars fully mix together. These encounters create some of the most dramatic structures in the universe. Long tidal tails of stars can be drawn outward into space, forming luminous streams that arc across hundreds of thousands of light-years. Gas clouds within the galaxies often collide and compress, triggering intense waves of star formation. During these events, entire regions of the galaxies can ignite with brilliant clusters of young stars forming in rapid succession. Some of the most striking galaxies observed by astronomers today are caught in the middle of such mergers. Their shapes appear twisted and chaotic, their spiral arms stretched into long ribbons by gravitational forces. Yet even this apparent chaos is part of the natural life cycle of galaxies. Over time, the two galaxies gradually settle into a single combined system. The final result of such a merger often depends on the properties of the original galaxies. When two large spiral galaxies merge, the orderly rotation that once shaped their disks may be disrupted. Their stars scatter into many different directions, eventually forming a smooth, rounded galaxy dominated by random stellar motions. This process frequently creates elliptical galaxies, some of the largest stellar systems in the universe. But galaxy mergers do not only reshape galaxies. They also help fuel the growth of their central black holes. As gas clouds collide and fall toward the center of the newly forming galaxy, enormous amounts of matter may feed the central black hole. This can trigger powerful bursts of energy as material spirals into the accretion disk surrounding the black hole. For a time, the galaxy's core may shine with extraordinary brightness, releasing energy capable of affecting regions far beyond the galaxy's center. These interactions also influence the rate at which new stars form. The compression of gas during mergers often triggers intense starburst periods, when galaxies produce new stars at rates far higher than normal. But once the available gas is used up or expelled by energetic outflows, star formation can slow dramatically. The galaxy gradually settles into a quieter stage of its life, dominated by older stars and slower internal activity. Our own galaxy is not exempt from these cosmic encounters. The Milky Way has already merged with many smaller galaxies throughout its long history. Evidence of these ancient mergers can still be seen in streams of stars drifting through the galaxy's halo. These stellar streams are the remains of dwarf galaxies that were gradually torn apart by the Milky Way's gravitational pull. And the future holds another dramatic meeting. Our nearest large galactic neighbor, the Andromeda Galaxy, is slowly approaching the Milky Way. Although the two galaxies are currently about 2.5 million light-years apart, gravity is steadily drawing them closer together. In roughly 4 billion years, the two galaxies will begin a slow and majestic merger. When that distant encounter occurs, the night sky of Earth, if Earth still exists, would transform in extraordinary ways. Andromeda would grow larger and brighter in the sky over millions of years, eventually stretching across a vast portion of the heavens. As the galaxies pass through one another, tidal streams of stars would arc across space while new waves of star formation ignite within both systems. Eventually, the two galaxies will merge into a single larger galaxy, possibly forming a massive elliptical system. Astronomers sometimes refer to this future galaxy with playful names, imagining it as a new cosmic home formed from the union of two ancient stellar cities. But even this grand event will simply be another step in the endless evolution of galaxies. Across the universe, countless galaxies are interacting in similar ways right now, each encounter reshaping the cosmic landscape. Galaxies may appear timeless and permanent when we observe them through telescopes, but they are actually participants in an ongoing dance guided by gravity and dark matter. Their collisions, mergers, and transformations continue shaping the universe even today. As we continue drifting outward through the vast structure of the universe, it becomes clear that galaxies are not solitary islands scattered randomly through space. Instead, they gather together, forming larger and larger communities bound by gravity. Just as stars collect into galaxies, galaxies themselves assemble into groups, clusters, and enormous superclusters that stretch across unimaginable distances. These structures form the largest patterns in the observable universe, creating a kind of cosmic landscape shaped by gravity and dark matter over billions of years. Our own galaxy, the Milky Way, lives within one of these small communities known as the local group. Compared with the enormous clusters found elsewhere in the universe, the local group is relatively quiet. It contains a few dozen galaxies, most of them small dwarf systems that orbit the larger members of the group. The two dominant galaxies here are the Milky Way and the Andromeda Galaxy, both spiral systems containing hundreds of billions of stars. Surrounding them are smaller companions, including the Large and Small Magellanic Clouds, faint satellite galaxies slowly interacting with the Milky Way's gravitational field. Within groups like this, galaxies exert subtle influences on one another. Their gravitational pull shapes the motions of nearby companions, sometimes drawing them closer over time. Smaller galaxies may be gradually stripped apart as they orbit their larger neighbors, their stars spreading into faint streams that wrap around the host galaxy. These interactions are slow and gentle by cosmic standards, unfolding over hundreds of millions of years. Yet they are powerful enough to reshape entire galaxies. Beyond small groups lie far larger gatherings known as galaxy clusters. These clusters may contain hundreds or even thousands of galaxies bound together by gravity. In such crowded environments, galaxies frequently interact as they move through the cluster's gravitational field. The space between galaxies in these clusters is not empty either. It is filled with extremely hot gas that glows faintly in X-ray light, forming a vast atmosphere surrounding the cluster. As galaxies travel through this hot gas, they can lose some of their own gas through a process similar to wind stripping. Over time, this can remove the raw material needed for new star formation, leaving galaxies dominated by older stars. Many of the elliptical galaxies found in dense clusters are thought to have evolved this way. Their gas reservoirs gradually depleted through repeated interactions with their surroundings. Clusters themselves are not isolated either. They gather along the filaments of the cosmic web into even larger structures called superclusters. These immense regions of space can span hundreds of millions of light years and contain tens of thousands of galaxies. Our own local group is part of a supercluster known as Laniakea, an enormous structure that stretches across more than 500 million light-years of space. When astronomers map the positions of galaxies across these enormous distances, a remarkable pattern emerges. Galaxies trace out vast filaments that intersect at dense nodes where clusters form. Between these filaments lie enormous voids where very few galaxies exist. Some of these voids span tens of millions of light-years and contain only a handful of isolated galaxies drifting quietly through the darkness. This cosmic web represents the largest structure we know in the universe. It formed gradually as gravity amplified the tiny density fluctuations present shortly after the Big Bang. Dark matter played a crucial role in this process, gathering into filaments that guided the flow of ordinary matter. Over billions of years, galaxies formed along these invisible pathways, slowly building the grand architecture of the cosmos. Yet even as this structure grows more defined, another mysterious force is shaping the future of the universe. Observations of distant galaxies have revealed that the expansion of the universe is not slowing down as once expected. Instead, it is accelerating. Galaxies that are not gravitationally bound to one another are drifting apart faster and faster as space itself expands. The cause of this acceleration remains one of the greatest mysteries in modern physics. Scientists refer to it as dark energy, a form of energy that appears to permeate all of space and push the universe outward. While dark matter helps hold galaxies and clusters together, dark energy works in the opposite direction, driving the large-scale expansion of the cosmos. Over unimaginably long periods of time, this expansion will continue reshaping the universe. Galaxies belonging to different clusters may drift so far apart that their light will eventually become impossible to see from one another. The night sky of the distant future may appear far emptier than the one we see today. But for now, the universe remains vibrant and full of structure. Galaxies continue forming stars, interacting with neighbors, and drifting along the vast filaments of the cosmic web. The invisible architects, gravity, dark matter, black holes, and dark energy, continue guiding the evolution of the cosmos, shaping the future just as they shaped the past. And so, after drifting through billions of years of cosmic history, we arrive gently at the present moment of the universe. Around us, galaxies continue their quiet journeys through space. Some spin gracefully with bright spiral arms. Others glow softly as enormous elliptical clouds of aging stars. Many still carry the faint scars of ancient collisions, reminders of encounters that happened long before our solar system was born. Yet despite all this motion and change, the universe often feels calm when we look at it from Earth. The night sky appears still, almost timeless. Stars shine steadily. Constellations seem fixed in place. The glowing band of the Milky Way stretches across the darkness like a quiet river of light. But beneath that peaceful appearance, everything is moving. Every star in our galaxy is orbiting the galactic center. Every galaxy is drifting through the cosmic web. And the universe itself is slowly expanding, carrying galaxies farther apart with every passing moment. The scale of these movements is so vast that they unfold far beyond the pace of human life. A single orbit of our Sun around the center of the Milky Way takes about 225 million years. That means the entire history of human civilization has occurred during only a tiny fraction of one galactic year. When the dinosaurs walked the Earth, our solar system was in a completely different region of the galaxy. And long before that, the Sun had not even been born yet. Even our own star is part of a much older story. The atoms that make up the Sun, the Earth, and even our own bodies were forged in ancient stars that lived and died billions of years ago. Those stars formed in galaxies that were themselves still young, still assembling from smaller cosmic structures. When those stars exploded as supernovae, they scattered heavy elements into space. New stars formed from that enriched gas, and eventually one of those stars became our Sun. In this way, the story of galaxies is also the story of us. The carbon in our cells, the oxygen we breathe, the calcium in our bones. All of these elements were created inside stars that lived long before our planet existed. We are, quite literally, made from the recycled material of ancient galaxies. Perhaps that is why the night sky feels strangely familiar. When we look up at the stars, we are not only observing distant objects. We are seeing the origins of our own existence written across the cosmos. The galaxies above us are not separate from us. They are part of the same long chain of cosmic events that eventually led to life on a small blue world orbiting an ordinary star. And the universe is still writing that story. New stars continue forming in countless galaxies. Clouds of gas collapse under gravity, igniting fresh points of light in stellar nurseries scattered across the cosmos. Galaxies continue merging, reshaping themselves through slow gravitational dances that unfold across billions of years. Black holes at their centers quietly grow, influencing the flow of gas and the birth of future stars. Even now, as you listen to these words, light from distant galaxies is traveling across unimaginable distances. Some of that light began its journey billions of years ago, long before Earth had oceans or continents. It crossed the vastness of space, passed between galaxies and clusters, and finally reached our planet, where it enters telescopes and curious minds. The universe has been sending us its memories for billions of years. Every star you see is a message from the past. Every galaxy is a chapter in a story still unfolding. And although the cosmos is vast beyond comprehension, it is also deeply connected. The same physical laws that shaped the first galaxies continue shaping the world around us today. So tonight, as the stars slowly wheel above the Earth, the galaxies continue their ancient dance. Dark matter still holds them together. Gravity still guides their paths. Black holes quietly influence their centers. And the cosmic web continues stretching across space like an invisible network linking everything together. You are drifting through that universe right now, carried on a small planet orbiting a modest star inside a spiral arm of the Milky Way galaxy. A galaxy that itself is part of a group of galaxies drifting through an enormous cosmic web. A tiny place, perhaps, but also a remarkable one. So as your thoughts grow softer and the quiet rhythm of the cosmos settles around you, remember that you are part of this vast story. The universe that built the first galaxies also built you. And long after we fall asleep tonight, the galaxies will keep spinning, the stars will keep shining, and the silent architects of the cosmos will continue their patient work among the endless sea of stars. Rest well, traveler. The universe will still be here when you wake.